To the second week of our course involving data merging. Last week we went over kind of the fundamentals of R functions and pertaining to data merging and loading data, exporting data. And this week we're going to get into the more interesting part of different joins and subsequent granularity. These terms may not be as familiar to all of you, but don't be intimidated. I'm sure everyone will grasp it quickly. So let's get started. So data joins. Anyone who may have some experience or knowledge about SQL, this is ingrained in all of databases and database tables. You have to join data to get ancillary information from other tables. It would look really bizarre if we had one table with a bunch of information in it with multiple duplicate rows, as there could be many values per person or per row. And so in the absence of that, it's really important that we understand how to join data from different tables. And there are four primary joins that we'll go over. There are a couple others, but they have really weird use cases, and I don't think that we'll really encounter them at any point in our in our exercises or anything that's traditional in joining data. So to get started, there is a sense of uh, ordinality in tables. We have to understand that although they are just pieces of data living in our computers in temporary files or in weird locations, when we go to join two tables together, there has to be a left table and a right table. Doesn't matter what order. There's no requirement that one table has to be left, one table has to be right. It's all based on preference. And so we could think of the left table as the primary table, the table that will most likely keep the most columns from. That way, we could think of everything as this is what we have, and we need to get this information over to that table. And with that, the left join is probably the most commonly used join. It keeps all the data in the left table or our primary table, and will join all of the data from the right table where the join keys match. So as you can see here in the Venn diagram, we have our primary table, table A, and we're going to keep everything in there. And then, where that intersects with table B, we're going to bring that data over as well. So here's an example. We're going to be using our hospital sample data. And here we have our left table, the hospital locations. And this has information for the hospital ID, the hospital, the name of the hospital, what city it is, and what county it's in. And then the right table is going to serve as the beds. So as you notice here, not every table that's in this hospital location table, or not every table, not every hospital that's in the hospital location table is in the hospital beds table. So when we perform a left join, and we're going to join here on this hospital ID, we're going to get a resulting data frame of everything that was in the hospital location table plus the med-surg beds. And here, you notice that there is another column for hospital over here. And for the sake of this, brief exercise, I excluded it out, but, traditionally, if you just join on hospital ID, this column will come over as well, and it will get this little weird suffix of y, and this one will have x, but we'll dive deeper into that later on. But for the sake of this exercise, I just wanted to focus on the med-surg beds being in this right table, and the hospital location table, getting that column appended over here based on just a join on the hospital ID. And next, the inner join. This is also very commonly used, and it is the default to many merge or join functions, whether that be in R or Python. In SQL, you have to spell everything out, but in programming languages, it's kind of the default. So if you were to just perform a function to say, hey, merge this table with this table, and you didn't throw an argument in there to say left, right, whatever, it will just default to an inner join, and they're great, but you may notice that you'll miss some of the data because the only result will be what intersects between both tables. So um, in this case, it honestly doesn't really matter necessarily as much which table is the left table or the right table, although there is, it is important still, because the output is going to be just everything that intersects. And so here, again, back to this hospital utilization data, we have our left table here of the hospital locations, and the beds are over here on the right table. And if we performed an inner join, remember if we go back, there was a bunch of blank values here because the tables that were in this left table, or the rows and hospitals that were in this left table, were not in this right table. Therefore, they did not have any values here. When you perform an inner join, since all of the data that's in the product, the output, has to intersect into both tables, we only get 5 rows here because there's only 5 values that are in both tables. And so this is great if you want to, kill two birds with one stone and just get it out of the way. And, your output, you only want those with values in, with MedSurg beds in the output. This is great, but in areas of, performing these tasks without, needing a condensed output, you typically wouldn't want to use an inner join. And, lastly, the right join. This is the complete inverse of a left join. It's essentially the same thing as just switching the order of the left table and the right table without doing that. So, we'll go over here and show you that these are in the same exact order, but instead, if we performed a right join, we would just, join over all of the data from this table onto the beds table where it intersects. And so we get these first, 5 rows here. Again, there's only 5 common hospital IDs in these two tables, so there's only 5 pieces of data as a result for the 2 hospital location columns that are coming over. And then a full join. This is going to keep all the data from both tables. And this gets a little murky, and I wouldn't recommend it in many use cases, although it does have its there are areas that you want to perform a full join, but most often it's not the best join type to use, but it's going to keep everything in both tables. And so here, we'll see that there is intersection where necessary, but at the end of the day, there isn't always a bunch of intersects, so you get this kind of table that there isn't really much of a structure to it. It just kind of fits in places and overlaps where possible. And with all these joins, as you noticed, there were a different number of rows each time we perform one of those joins in the examples. And so that output of how many rows there are per row ID or per key is the concept of granularity. And so there are 3 main types of granularity. There's a one-to-one relationship, a one-to-many, and a many-to-many. So in one-to-many, both sides of the relationship have unique values for every row. So that would be an example of, there are 2 tables and they both have 1 row per key. And when you join them, you're only going to get 1 row per key. The information just appends, naturally, and it's a very straightforward way of doing it. But let's say, there were more rows per ID in a right table, and the left table just has 1 row per ID. That would be one-to-many, where there's 1 value, per key in the left table or right table, and then there's many values per key in the other table. And so that's one-to-many, and then if both tables have multiple values per key, that's a many-to-many relationship. And so this is a good example of a one-to-one relationship where this column has 3 IDs, 3 unique IDs, Alice, Bob, and Kathy, and then the other table has 3 IDs. They're both identical. And so if we were to perform a left join we would get 3 rows in the result because there's only 3 unique rows and they're all unique IDs. But now if it's one-to-many, so let's say there are multiple values per row or per key in one table and not another. This is one-to-many. So this is an example of, let's say we had to merge a file of patient encounters to another file with patient demographics. Well, in the patient demographics table, we would have 1 row per patient. Patients don't have many demographics that their demographic information will be, for the most part, mutually exclusive. So, think of gender or age. You could have multiple ages or multiple genders. You will identify as one thing, or you only have one age. But however, if you're going to merge that with an encounter table that has, let's say that patient has 4 encounters, that the keys that you're going to merge on are going to be duplicated in one table, and there's only going to be one in another. So when you left join on that, the result is going to be the number of rows per unique key in the table with multiple keys. So to give a visualization, we'll use this car engineer table, and so here we have two unique cars, and we have multiple engineers. Now, multiple engineers can work on those unique cars. And so if you were to join, who worked on the Toyota Camry, there are 2 engineers with the Toyota Camry. So while this ID is unique, there's just 1 row per unique car ID in this table. There are multiple rows of the unique car ID of 2 in this table. So if you're to join over, and let's say you're joining all of the engineer information to the car, your output will have 2 rows for the Toyota Camry and 1 row for the Benz. And so your output will be 3 rows instead of just 2, no matter if you use this as the left table or the right table. And then a many-to-many relationship, this is where you have multiple rows, per unique ID in each table. And so here we have the example of you have encounters here for patient IDs, and then you have a patient ID in this table over here with multiple rows per phone number. Patients can have a home phone, a work phone, a cell phone, and they can have multiple encounters. So, as you can kind of see, if we were to join this information and link all that information together, the output is going to have a ton of rows, because if we just join on patient ID is equal to patient ID, then we're going to get 3 rows for just this encounter, 3 rows for this second encounter, 3 rows for this third encounter, and that right there is going to give you 9 rows. And so your database can get a little long, which is why or your resulting data set can get a little long, which is why we went over filtering and stuff like that in the first lecture. And if you remember, I prefaced it by saying it's useful to filter beforehand so that our output will be very just concise. And so a good practice here would be if the question is, hey, can we have all the cell phone numbers for each encounter, we would filter this table first for just cell phones, and then we perform the joins, and our output would just be the same as we have here, because we're just going to get one value from this the right table for each unique value in the left table. And so merging in R. So now that we understand kind of how this works and different type of joins and why we'll do it and how to do it, it's now time to figure out, okay, how does this get executed in R? And it's all through the merge package. And it's in base R. So whenever you download R, it's just part of the R software. And so all we have to specify is X, which is going to be our left table, the primary data frame, Y, which is going to be the right table or the data to merge onto the primary table, the type of join. So um, we're going to say here it's a little different. It's not as straightforward as, let's say, Python. So an inner join is just going to be all equals true as one of the arguments up here in parentheses. A left join is all x equals true, and that's going to be, again, just another argument. Or we can have all y equals true, which is just a right join. And so the x is the left table and the y is the right table. And then we'll just have to specify. So here we'll say by x. So if we're merging on patient ID equals patient ID, we can say by x equals patient ID and by y equals patient ID. Or we can, just scrap that, instead of saying it twice, if the column is named identically in both tables, we can just say by equals patient ID, and R will understand, okay, both tables have to have this column, and so we're drawing on that column for each table. And here's just an example of how to do this. Just a quick brief overview of the syntax. These are just dummy data frames. So say we make up a data frame, and these are all column headers. So there's a column called key, there's a column called A, and a column called B. And then the values in the key column are K0, K1, K2, K3. And if we made another column over here called right, we have the key column again, the same values. And then we just have different column names for the rest of the ancillary data. So C and D. Now, if we wanted to merge this fake left table to this right table, we can just we give a variable. So merge data frame is going to be equal to merge the left table called left and the right table called right, and then by is the key. They both have a column called key, and you would get the result of all of this data will stay here, and then it'll merge over C and D, and then your output column will be a column called key, A, B, C, and D in your data frame with 5 columns in total. And so, this is just a brief overview. We'll go over, these concepts a little bit more in depth in our class together, and take it to another step and start executing some of this code in R. But this video is really just to give you a brief, demonstration and explanation before we get into class of how these joins work and when we would typically use them. And the readings for this week will also supplement the purposes and functionalities behind the joins. And so yeah, looking forward to working together in class, and talk to you guys soon.